Chapter 10, Section 1. Here we are going to see some curves that are defined by parametric equations, see what it is and how we draw them easily, and we will see several examples of this. So this is essentially easy small section with some curves that are interesting, and then we are going to try to draw them properly. So what is a parametric equation? So essentially what we have is a variable t, a parameter, and then we have a function of that parameter as coordinate x of a point and as a coordinate y of a point. So essentially we are in 2D, we are in plane xy, and then the coordinate of a point in x is given by some expression, usually a function of parameter t, and coordinate of the y component of the point is given by some expression which is also a function of t. So we will see several examples of that. So this could be cosine t and exponential t, let's say. So essentially each time the value of parameter changes, the value of the function in x will change and value of the function in y will change. So we will have a different location in xy plane for each value of parameter t. So t is a parameter and these are parametric equations. So essentially these equations will give us location of a point for a certain value of t. We can think of t as time. In most situations that will be time, but it doesn't need to be. It could be angle, it could be something else. What we will get every time is a curve in a xy plane, so that's why it's called plane curve. And you will see those curves are not functions most of the time in our examples. So this expression here, okay, it's a mysterious expression. So this is a curve in a plane xy, so in 2D. Obviously it's not a function, it doesn't pass vertical line test. So for one value of x we have several values of y, so this is not a function, it is a relation. So we call it plane curve because plane xy is where this curve is living, and we can think of it as a path of a particle that is moving. So you can have, let's say, a car moving on a road or a particle moving in a fluid somewhere or in the air, doesn't matter. So it's essentially a particle moving along a path. So each time t, the parameter, changes value, the component x will change and component y will change and particle will move. So now we need to see also the direction of movement. How do we do that? Well, it's very easy. We take two consecutive values of t. Let's say t equals 0, we find a location on the curve, and t equal 1, we find another location. So we know that as t increases, the particle moves in a certain direction. So that's very simple, straightforward. So we can see that these curves are not functions, and we can think of them as paths on which particles move. So that's very useful as interpretation. So again, t is a parameter and these curves are called parametric curves or plane curves because they live in a plane. And again, we think of it as motion of a particle along a path. And as t increases, we will get the direction of movement. Here, t could be interpreted as time for our purposes, but sometimes we will see in examples it will be angle because something is rotating. So it doesn't really matter is it time or an angle or something else. In some occasions t will be free, so it can take any real value. In other occasions, depending on the expressions, it might have some limitations on t. So let's say if t can be negative, we can think of it as something that happened in the past, for instance. If we have an interval for t, so let's say t is between minus 2 and 75, so we have an interval for t. That means at t equal minus 2 we have initial point, and at t equal 75 we have a terminal point. So that would be a finite curve. Or we can have a situation when there is no restrictions on parameter t. In that case, t can take any real value, so positive, negative, 0, it's fine. And in that case we can have, again, depending on the situation, some curve that is infinitely long, or some curve like a circle, for instance, that has specific length. So if the bounds are given, we know we have initial and terminal points. If the bounds are not given, it will depend on the situation, if we have initial point and final point. In some situations, we are able to eliminate the parameter. Essentially, we can, from the equation for x, we can somehow rewrite it so that we have an expression for t, and that expression is then replaced into the y, so that way we eliminate the parameter t, actually. Ironically, most of our problems, we are able to do that. But in general, in many cases, we are actually not able to eliminate the parameter, so the parametric equation will stay as they are. But in case where we can eliminate the parameter, what we will get is some type of a Cartesian expression of x in terms of y, or y in terms of x. So we will have an equivalent Cartesian expression for our parametric curve, and we will see several examples for this. Obviously, it's easier to draw these curves using computer, but again, we will try to draw them on our own. For something this complicated, computer is very useful. Now, here, what is interesting is to realize that x is a function of y. Okay, we are used to expressions y equal some function of x. Well, here it's the other way around, and we realize that this is not a function. The curve that we get is not a function, it is a relation, because for one x we have several y's. Now, how do we write it as a parametric equation? Well, we can just identify one of the variables as t. In this case, y is convenient to call t, and then x is another expression in terms of t. So this gives us two parametric equations, and parameter is t. This is just a simple example how to rewrite it, nothing special there. Another interesting example that we will see more in 10.2 is cycloid. So essentially we are going to be able to compute the length of this arc, and then the area between the arc and x axis and stuff like that, but that will be in 10.2. For now, what we want to see is a little bit the shape, and again, the shape of this curve is obtained if you take a circle of a certain radius r. Think of a wheel of a car of certain radius, and then you roll it simply on x-axis, or you roll it on the pavement. So what happens is that specific point that you picked on the curve, on the circle, is tracing a curve, and that curve is called cycloid. So essentially you have, let's say, a dot on your tire, and then you observe that dot as the tire rolls along the road. So what you get is these arcs here. So obviously we can treat theta as an angle of rotation. Instead of thinking of time, we can think of the angle. So what we see here is that we have a pattern that keeps repeating forever. So this one arc is obtained when the wheel rolls from 0 to 2 pi in terms of the angle, so one rotation. So one arc of cycloid is obtained when we roll from 0 to 2 pi. So essentially you have here a circle and then a point on the circle, and you follow the point. Now later on we will be able to compute the length of this cycloid. It will be 8 times r. For now we don't know how that's computed. We will learn in 10.2. But that's something that is interesting. The curve that you obtain by following a point on a rolling circle. It's called cycloid. Now, some applications. The weird thing, if I have 2 points, for instance, this is just an illustration. I have 2 points and then I let a ball roll from A to B, and I would like to know which path will produce the shortest time. So the ball will roll, let's say the fastest, will take less time to go from A to B. Which of these paths, straight line or some type of a curvy path? It turns out that inverted arc of a cycloid gives us the path with the shortest time of running from A to B. So that's something curious. So this cycloid that we get here, if we flip it, essentially we have an arc of a cycloid and then inverted. So that would be the path that would produce the shortest time from A to B if we run a ball along it. Another interesting application is with the pendulum clocks. So essentially, if we have inverted cycloid, let's say I start rolling a ball from this point and I measure the time it takes to reach the bottom. And then I take the same ball and leave the roll to roll from this point to the bottom. So if I am on the inverted cycloid, the time that it will take for the ball to roll from this point P to the bottom is the same time as the ball will take to roll from this point here to the bottom. So that's very interesting. So that's why this is useful for pendulum clocks. So essentially, no matter from where the pendulum starts swinging, it takes the same time to reach the bottom point. So that way we keep the same time. It's amazing. So this cycloid is very interesting curve. Now, obviously, we want to be able to draw some curves on our own. So how do we do it? Well, usually we just produce a table with dots. So essentially, if I want to sketch a parametric curve, here I have an expression for x, an expression for y. So x and y are coordinates of a point, and t is my parameter. We can think of it as time if we want. So my parameter runs from -2 to 4. So I have lower bound and upper bound of my parameter, which will produce certain couples here for x and y. So the easiest way to proceed is to draw a table, essentially evaluate these expressions at certain values of t. So between -2 and 4, we could have increments of 1 and then produce the values. So at t equal -2, we have 6 minus -2 squared, which is 4, so 6 minus 4 is 2 here. And then we plug t here -2, in y we get -1, so here it is. So at t -2, the point is 2 minus 1. So point here 2 minus 1. And then so on, we plug some different values for t, -1, we plug it here, so 6 minus 1 is 5, and then here -1 over 2. So that's a point here. Immediately, as soon as I have 2 points, point corresponding to -2, point corresponding to -1, immediately I can know the direction of movement. So essentially, with 2 points following the movement, I know how the curve works. And also what we see is we have starting time, so the starting point, and we have the final time. So at some point we have final point. It is interesting to observe that, let's say here at the point 6,0, which corresponds to time 0. So when t is 0, x is 6, y is 0, we have a vertical asymptote. So later on we will ask questions, where do we have vertical asymptote, where do we have horizontal asymptote, things like that. Obviously we will want to compute, let's say, a slope of a tangent line at specific point for some value of t. We will get the point, and then we want to know what is the slope of the tangent line, for instance. For now we just want to draw these curves. Later on in 10.2 we will compute these other things. So for now, easy thing would be just to produce a table for different values of t. We get couples x and y that are coordinates of points, and we just connect the points together, and then we have a shape of the curve. So that's in general. Now in some cases, like in this one, we could eliminate the parameter t. So here we have y is equal t over 2. So t is equal to y. So instead of t, I could use 2y into this expression, so I'll get something that I can recognize. So in this situation, we are able to eliminate the parameter t. So you see t is equal to y, and I plug it and I get something like this. So this is an expression of a parabola, which is the same as this one, obviously. Now what's special about it, it is something that we are able to recognize a little bit. Now this is a parabola and it's defined for all values of y, obviously. Now in our case, t is the one telling us that t goes from -2 to 4, so y cannot just be any value, it needs to respect some constraints, conditions. So while by eliminating parameter we get some familiar expression that helps us maybe draw the curve, we still need to go back to our constraints on our parameter in order to know what are the starting and end point for our curve. So by eliminating the parameter, what we learn here is we eliminate some information also. Yes, we get an expression that is more familiar, so maybe easier to draw, but we lose the information on the bounds. So we always need to keep both of them. This helps us, this expression where we eliminate the parameter helps us maybe recognize the curve, but we always need to go back to the values of t that will produce, gives us information about initial and end point on x and y. So this is important. So eliminating the parameter helps produce an equation that is more familiar, but we need to still go back and inform ourselves about the conditions or constraints on the time so that we know what are the starting and end points. And as we said, the orientation of the curve, the direction in which particle moves is determined by just comparing the value of for two consecutive values of time. We compute two different locations on the curve and we see in which direction it goes. So that's quite straightforward. Another example, again, we here could produce a table and then draw the curve, but we can also maybe eliminate the parameter. So now what we see is we have a curve defined by two parametric equations. So this equation gives locations in x and this in y. So for a specific value of time, let's say t equals 0, I'll have x 0 and y 1. For t equal 1, I'll have -1 in x and y is equal to 2. So I'll have two different points immediately and I can connect them. Now what we observe here, there is no restriction on t. So we don't have an interval for t, which means t could be any value. Now also sometimes will happen in some examples that the expressions for x and y give us some constraints on t. Let's say, imagine we had radical here, radical t plus 1. So we know that under radical we cannot have a negative number, so that would produce a constraint. In this situation there is no restrictions on t, so there is no restrictions on x and y. They can go as big as we want. Again, we can compute several values. For several values of t we can have different values of x and y, the couples, and then plot those on in a plane xy and then connect the dots. And again we have, let's say here, -1, at t -1, the point is 3, 0, so 3, 0 is here. At t0 the point is 0, 1, so 0, 1. So we went from here to here. That gives us immediately the direction of the movement. So once we have the direction of the movement, it's the same for the entire curve. So how do we determine the direction? Well, we take two consecutive values of t and we see to which points they correspond, and we go from lower value of t to higher value of t, and then we get the direction. Now again, in the expression we had y equal t plus 1, so we could actually rewrite it as t equal y minus 1 and then replace this expression into x, which gives us a more familiar expression. So again, here x is equal to a function or expression of y. So this curve is not a function because it doesn't pass the vertical test. So vertical line here, for the same value of x we have two different values of y, so this is not a function, it is a relation. So this plane curve, it's maybe easier to draw it this way. Again, to draw it we can just list points, create a table like we did here and connect the points, or when possible we could eventually eliminate the parameter, which means find a simple expression and then write t as a function of y or x depending which one is easier, and replace it into the other expression. Here we have the same expressions, but t is limited from 0 to 4. So previously t was free, so we had a curve that goes all the way. Now if we have t going from 0 to 4, starting point is t at 0, so that's x0 and y1, so x0, y1, and then the next point we take, let's say t equal 1. For t equal 1, x is -1, y is 2, so x is -1, y is 2, so we are here. Then t equal 2, we get x equals 0, y equal 3, so x equals 0 and y equal 3, so point here. So again we get just one part of the curve. So it's important to check always the restrictions on t. So we in this situation have a starting point and end point because t is living in an interval. In other situations we could have some familiar functions. So let's say x is given by cosine t and y is given by sine t, and then t goes from 0 up to 2 pi. So we have a curve, plane curve, so it will be in y-x plane, and the coordinates for the points are given by these two parametric equations. So now we can wonder what could be this curve. So obviously again we can draw a table with different values of t, compute corresponding values of x and y, and put the dots on the graph and then connect the points. So that there is nothing wrong with that. However, we can also observe that if I have x squared, which is cosine square, plus y squared, which is sine square, I'll get 1. So actually x squared plus cosine x squared plus y squared is equal to 1. So this reminds us of a unit circle, so circle that is centered at x equals 0, y equals 0, and of radius 1. So that gives me immediately the shape of the curve. it is a unit circle centered at 0. Now, what I don't know is what is the direction in which the particle moves along this specific circle. So what's the starting point? Well, starting point is at t equals 0. At t equals 0, cosine of 0 is 0. No, cosine 0 is 1. Sine 0 is 0. So x will be 1, y will be 0. So x will be 1, y will be 0. So this is a starting point. Now my t goes from 0 to 2 pi. So I need another value for my t. So an easy choice would be, because here I have cosine and sine, pi over 2. So at pi over 2, cosine is 0 and sine is 1. So at pi over 2, cosine is 0, sine is 1. So we are here. So you see we started at 1, 0, and then as t went from 0 to pi over 2, we reached the point here on the curve x0, y1. So we have direction of movement, and it is counterclockwise. So the particle starts here and it spins counterclockwise once. Again, this is a circle. Center is x0, y0. Radius is radical 1, so 1. And we spin only once, and we turn out to spin counterclockwise. Beautiful. So that's what we can do. From a parametric equation, find some familiar curve, so it gives us an idea of the shape, and then we evaluate the expression at two different values of time to get the direction of movement of a particle. Now this is similar, but in this case x is equal to sine and y is equal to cosine. So at t equals 0, sine 0 is 0, so x will be 0 and cosine will be 1. So the starting point is not the same. Again, if I take x squared, I have sine squared, y squared is cos squared, so if I add them, I get 1. So again, my curve that I get, the plane curve, is a unit circle centered at 0, 0. However, the starting point is not the same. Here the starting point will be 0, 1. So we see here the starting point was 1, 0. In the new situation, starting point will be 0, 1, so we will start actually from here. If we swap sine and cosine, we start here. So that's interesting to observe. Now, what happens if I take t equal pi over 2? So as time increases, sine will be 1, cosine will be 0. So x is 1 and y is 0. So we started up and then we are going this way. So that means it is clockwise. So it is simple. In both cases, we have a unit circle. However, the starting point is not the same and the particle doesn't move in the same direction. So you see the difference. Even though in both cases we have the unit circle as a curve, shape of the curve, the movement of the particle is not the same and the starting point is not the same. So by, in a way, eliminating the parameter, we lose some information. So that's why it is important to go back always to our original expressions to figure out the movement of the particle, in which direction it goes. Another example here, sine 2t and cosine 2t. Here t goes from 0 to 2 pi. What we will observe again, if I square both of them and I add them, it's again unit circle. So this is third time I get the unit circle as a shape, and it's centered at 0, 0 and radius 1. Beautiful. Now, what's the difference in this case? Well, 2 here is actually a frequency. We know that when I have sine t and cosine t, when t goes from 0 to 2 pi, I spin only once around the circle. But now I'll spin twice. So this is a frequency at which we spin. So again, we start at the point 0, 1. If I plug t equals 0, I'll get sine 0 is 0, cosine 0 is 1, so 0, 1. So I start here, and then the next point, if I take, let's say, pi over 4, I'll get sine pi over 2, which is 1, and cosine pi over 2, which is 0. So I'll be here. So essentially I know that my particle is running clockwise, but it will go twice around. 2 is the frequency. If I had 3t and 3t, my particle will spin 3 times around. So that's the situation. So essentially the shape of the curve is the same, but our original expressions tells us what is the starting point, in which direction the particle is moving, and how many times. This is another example again. So here the frequency is 1. So if I go from 0 to 2 pi, I'll go once around the circle. Now I only need to figure out what type of circle this is. So maybe it's a circle with radius 2. Let's see. And then the other part of the question, t is going from 0 to pi only, not to 2 pi. So maybe it's going halfway. So that's what we need to see. Again here, if I square x squared plus y squared, I'll get 4 cos squared plus 4 sine squared, which is equal to 4, right? So in this situation, I have a circle centered at x0, y0, radius radical 4, so radius 2. So the center of the circle is 0, 0, radius is 2. What's the starting point? Well, here at t equals 0, what do I get? Cosine 0 is 1, so I have 2, 0. So starting point is 2, 0. So 2, 0 is here. And then as t increases, my particle is moving up. So it is counterclockwise. So my curve, parametric curve here, or plane curve, is a circle centered at 0, 0 of radius 2. Starting point is 2, 0, and the particles are moving counterclockwise. And we run only one time around the circle as t goes from 0 to 2 pi. Beautiful. Now what happens if 0 goes from 0 up to pi? Well, we'll get only the upper part of the circle, so the upper part of the half circle, essentially, that's what we get. And again, frequency here is 1, 2 is the radius in this situation. Okay, so these are simple things. Here is maybe a more general situation where I have here the radius, and then h and k are the coordinates of the center. So this is a more general formula for the center of the circle and the radius. And again, how do we get it? We bring h on the other side, so we have x minus h, y minus k, and then we square everything, so we get x minus h squared plus y minus k squared equal to r squared. So essentially, that's how we figure it out. Now, if we want to identify some of the curves, obviously we need something relatively simple. Here t goes from 0 to 2 pi, and we need to see what's happening. Here immediately in B we recognize something. It's going to be a circle of radius radical 4, which is 2, and center 2 and 3. This is what it looks like. So, but let's start with A. What we realize, we have 2 sine t and 3 cosine 2. So the numbers here are not the same. So this is not a circle. If we had 2 and 2, it would be a circle. If we had 3 and 3, it would be a circle. But 2 and 3, it's not a circle. So it's something else. So it turns out it is an ellipse. So how do we get there? Well, what we know is that sine squared plus cosine squared is 1. So x divided by 2 is equal to sine t, and y divided by 3 is cosine t. So now we square both of them, we add them, the result is 1, right? Sine squared plus cosine squared is 1. So we have x divided by 2, everything squared, so x squared over 4, plus y divided by 3, everything squared, so y squared over 9, so that's equal to 1. This tells us that this is an ellipse, center is x at 0, y at 0, and semi-axis in x is radical 4, which is 2, and semi-axis in y is radical 9, which is 3. Now, how is this curve traversed? By a particle, so at t equals 0, sine is 0, so x is 0, and here y is 1, so x is 0, y 1, so we start over here. Oh, sorry, x 0 and y is here 3, because 3 times 1. Okay, and then what happens if I increase from 0 to, let's say, pi over 2? Sine at pi over 2 is 1, times 2 is going to be 2. Cosine pi over 2 is 0, so y will be 0 and x will be 2. So x is 2 here and y is 0, so we start from here and we go clockwise. So that's what we can figure out quickly. Now, as we said, we suspected that the second curve was a circle, so x minus 2, y minus 3, so we get equal to 4 cos and equal to 4 sine, so we square everything and we get this expression here. So it is a circle centered at 2, 3, so x is 2, y is 3, so that's the center, and the radius is radical 16, so it's 4. So we get a circle centered at 2, 3, and radius 4. Now, how is it traversed? Well, if we start at 0, we get cos at 0 is 1, so 4 plus 2 is 6, so x will be 6, and y will be 3, so we start somewhere here. And then as t increases, let's say pi over 2, this part will be 0, so x is 2, and y will be 4 plus 3 is 7, so we will be somewhere here. So we see we started at the point here 6, 3, and then we went all the way up to the point 2, 7. So we are turning counterclockwise. And the last example here, what we see is 3 and 3, so this is going to be a circle, but we have 2t, so this will be traversed twice, so that's a frequency at which we spin around. So again, the curve is x squared plus y squared is equal to 9. So it is a circle centered at 0, 0 with radius 3. And we are traversing that circle twice because this is a frequency. Now the starting point will be 3, 0. And then we are going counterclockwise. How do we know that? But if I take t equal pi over 4, for instance, then pi over 4 times 2 is pi over 2, so cosine will be 0 and y will be 1. So I have x 0 and y equal 3. So that way I see that is going counterclockwise. And again, how do I know it goes twice? Well, this is 2 is the frequency, how many times we spin around. Another interesting case is if I have a task to find a parametric equation for a segment of a line. So at t equals 0 we are at this point, at t equal 1 let's say we are at this point. So I need a segment, line segment, which means it's a line in x and a line in y, so we want to have some linear expressions here, so we need to find a, b, c, d. How do we do it? Well, at t equals 0 we need to be at point 1, 2, and at t equal 1 we need to be at point 4, 7. Simple. We just solve that. At t equals 0 at t equals 0, x is equal a, and y is equal c, which is equal to 1 and 2. So a is 1 and c is 2, simple. And then at t equal 1, we need to be at 4, 7, so essentially we solve this, and we get the expression, so nothing special there. So now, what is the parametric equation for the parabola of this sort? So this is y equal x squared, fine, but it's from the point negative 1, 1 up to 0.39. So it's not the entire parabola, is just one part of it. So the simple way is always to define one of the variables as t and the other one will be in terms of t. So here x, if x is t, then y is t squared, simple as that. So that's our parametric pair of functions. And then in this situation, time will go from -1 to 3, y, while we need -1, t minus 1, and then -1 squared is 1, beautiful, and then t equal 3, and then 3 squared. If we need to sketch these curves, so these curves are actually similar but not identical. So let's see a little bit what's different. So obviously we can just have a table with different values of t and then have couples x and y corresponding to those values of t and then put the dots and connect them. In this situation we can also eliminate the parameter, so to have maybe a nicer expression that we can recognize. So just to see here, x doesn't have any restrictions for t, so t can be any value, and x will be positive or negative depending on the values of t. And here y, t squared, so t squared is always positive, -2. So the smallest value for y will be -2. But x can take any value from -infinity to infinity. Right? Just observation. In contrast, in situation B, t again is free, can take any values, it's fine, but x, its lowest value will be -1. And after that, it will grow. Regardless if t is positive or negative, x will be going from -1 up only. So x will be from -1 up. Interesting. Y, so t to power 4 obviously is positive, -2. So this, again, the smallest value will be -2. So in y, we'll start from -2 and we'll go up. So that's interesting, it's different. Here x can go from -infinity to +infinity. Here x goes from -1 to +infinity. So that's different. So these two curves are actually different. We see it immediately. Even though you will see they look similar. So in the first case, again, there is no restrictions on t, so t can run from -infinity to +infinity, is not an issue. We can here eliminate the variable t is equal to x plus 1 and then plug that expression for t here in y and we get a parabola here. So it's nothing special. What we realize is x again goes from -infinity to +infinity and y is going up starting from -2. So nothing special, all good. Now the expression here, we said t can be anything, but x will go from -1 to infinity. Again, we can isolate t squared, so we can replace it. So we get a similar expression, right? X plus 1 squared minus 2. X plus 1 squared minus 2. So it looks like we have the same type of a parabola. However, as we noticed, so we need to go back to our expressions for x and y, we noticed that x, for any value of t, so the smallest value of x is -1. So x goes from -1 up. X goes from -1 up. So we only have one part of the parabola. So even though the Cartesian expression is the same, the restrictions on x and y are different. So here x needs to go from -1. We observed that. So it's important when we eliminate the parameter, we get an expression that is more familiar, so it's easier to draw the curve. But we always need to go back to the expressions in x and y to see what are the restrictions. So here we realized that x needs to start from -1 up. So we only have one part of the curve. So that's what is interesting. These parametric expressions will code for different parts of the curve. So that's also an interesting thing. Another interesting expression is we have the same Cartesian expression, which is this one. So technically, if we draw it, we get only one type of a curve. However, if I interpret my parametric equations as path of a particle, we could write different expressions whose Cartesian equivalent is this, still always. So let's say x is equal to t cubed and y is equal t. So if I put y equal t and then x will be t cubed. So there's nothing special there, straightforward. If I say that y is equal negative t, then x is equal negative t cubed. Okay, so again I'll have x equal to y cubed. So nothing special. It's always the same Cartesian expression, but we will see that these two curves are a little bit different. They are not traversed in the same direction. And then this one is a little bit more creative. We could say that y is radical t. Oh, so in these previous situations, t could take any real value. But in this situation, t must be greater or equal to 0. Oh, not the same thing. And then I cube it, I get my x. So now again I have this expression here. So the same Cartesian expression gives me different types of parametric equations. So this is just an exercise to see a little bit the implication of it. And then we can get creative. Y equal exponential negative 3, and then we cube it, so we get exponential negative 3t for x. And what we realize here, regardless of the value of t, x is positive and y is positive. Bigger the t, closer we are to x0 and y0. See? So the same Cartesian expression, and we have 4 different behaviors. So 4 different plane curves, parametric curves. So let's see the shape of it, just quickly. So our first one, y equal t and x equal t cube, is this shape here. So essentially it looks like the third root, right? And it is traversed from left to right. If I plug y equal minus t, then x minus t cubed, so it still respects this Cartesian expression. Then I have the same shape, but it is traversed from right to left. So it's not exactly the same thing, huh? Its shape is the same, but the particle is traveling in first case from left to right. In the case B, it goes from right to left. So description of the movement of the particle is not the same, even though the Cartesian expression is the same. So you see the richness of and usefulness of these parametric equations. It is encoded in them not only the shape, but also the direction of the movement of the particle. It is intrinsically encoded inside this parametric expression. The thing that we don't see here, we will here only get the shape, but we got no idea where the particle is going. Whereas if I have these parametric equations, they'll give me the shape of the curve and the movement of the particle. So there is something extra there. So it's not just futile exercise, it's interesting. Third case was radical t. Immediately we know that y needs to be positive, and t needs to be greater or equal to 0. So at t equals 0, y is 0, x is 0, so we start here. And then as t increases, y goes up and x goes up, so we are here. So we have only one part of the curve, and it starts at 0, 0, and it keeps increasing. So the particle is having a source at 0, 0, and then it's traveling along this curve. Now what happens if I put y equal exponential negative t, then x is exponential negative 3t. As we said, both of them are positive, so now regardless of what's happening, if I take positive value of t, I'll have exponential negative and exponential negative. So bigger the t, closer I am to 0, 0. And I will never reach 0, 0 because exponential is never 0, right? So bigger the t, closer I am in x to 0 and closer I am in y to 0. So I'm closer to the point 0, 0. So essentially we are going this way. So that's interesting. You see the same Cartesian expression, but we have different parametric equations that describe different paths of particles. So this is just interesting to observe and to realize that these parametric equations actually are rich in information. They give us the shape of the curve, but also the direction of movement of a particle. An interesting example again for a parametric equation. So we have a plane curve, but we need to figure out which curve it is. So x is sine t and y is sine square. So we obviously see that y is equal to x square. So y equal x square, we know how to draw it. It's a parabola, it's fine. Now, as we said, our parametric curves, parametric equations, they give a lot of information. Y equal x square, well, it's defined for all x's and all beautiful. That gives us a shape. That's fine. However, we need to go back to our original expressions to figure out what's actually the curve. So sine, regardless of value of the argument t, is between -1 and 1. So x's will be between -1 and 1, no choice. So x cannot be 10,000. You see y equal x square, I could take any x, right? But because of my expression here, actually I cannot. X needs to be between -1 and 1. Y is sine square. So regardless of the value of t, sine square is between 0 and 1. So x's are between -1 and 1, and y's are between 0 and 1. So suddenly, this restriction is encoded here in the parametric equations. So this specific plane curve is not actually y equal x square. It's just one part of it. One part for which x runs between -1 and 1, and y will run from 0 to 1. Again, these parametric equations are giving the shape of the curve and also restrictions, and they tell us how the particles are moving. So essentially what we realize is, regardless of the value of t, my x's will be running from -1 to 1, and y's will be running from 0 to 1. So we have only one part of the parabola y equal x square, and that part is traversed by a particle that is bouncing up and down. So this is very important. Having y equal x square helps us produce quickly the shape of the curve, and then we go back to the expression for x and for y and we realize what actually part of the curve we are on. So those are very interesting and important things to observe. This is maybe one example just to see a little bit the application, not so important maybe. And then we have several examples that are solved. There are many more for you to do. So let's say we have the parametric equations. Here we want to know what is the curve, so the plane curve, how it looks like, and what is the direction. So again, with this, what we can do, we can try to eliminate a parameter t, so rewrite expression for t and then plug it into y. So essentially we get this equation, which is equation of a line. So we know that here t has no restrictions, so it's a line going like this, so infinitely extended in both directions. So now the next thing is, what is the direction of movement? So let's say I take two consecutive values of t and see where the points are. At t equals 0, x is 2 and y is 3. So at t equals 0, we have points 2, 3. Okay, so at t equal 1, what do we get? Here 3 plus 2 is 5, and then here 2 plus 3 is 5. So we have a point 5, 5. So 2, 3, and then 5, 5 here. So essentially we know that we started here at t equals 0, at t equal 1, we are moving in this direction. So the direction of movement is up. Another cute example. So we have x is equal sine, y is equal 1 minus cosine. Oops. We know that sine square plus cosine square with the same argument is equal to 1. So we can rewrite this a little bit. So x is sine, that's fine. And then here we swap. Cosine is equal to 1 minus y. So now we can square those two expressions. So we'll get this expression here. So we have a circle, radius 1, center x0, y1, x0, y1. So this is a center, radius is 1. Great. Now we need to figure out the direction in which the particle is running. So at t equals 0, x is 0 and y is 0. So at t0 we are at 0, 0. And then let's say at t equal pi over 2, sine pi over 2 is 1, cosine pi over 2 is 0, so 1 minus 0 is 1. So we are at the point 1, 1. Okay, at t pi over 2 we are here at 1, 1. So we started at 0, 0 and we went up to 1, 1. So this gives us direction in which the particle is running. So it's running counterclockwise. And it's running only once because we see that the frequency is 1. Here in this situation we have x equal radical t. So we know immediately that t cannot be negative. Immediately from here. So t is greater or equal to 0. Good. So the smallest value for x is 0. And then here y, the biggest value will be 1, and then y keeps going down. As t increases, this will be negative. So quickly, I see that x squared is equal to t, so I'll have y equal 1 minus x squared. So this is a special parabola. So basically I see that x needs to be positive and t, its highest value is 1, and then everything else goes down. So essentially we start at point t equals 0, so x is 0, y is 1, so we are here. At moment t equal 1, x is 1, y is 0, so we are here. So we know what's the direction. So rewriting or eliminating the parameter helps us maybe get an idea of the shape of the function, but then we go back to the expression to get the direction of movement of a particle. Here similarly, what we realize is x is t squared, so x needs to be greater or equal to 0 regardless of the value of t. Y can be positive or negative. So if t is positive, y is positive. If t is negative, y is negative. And here we don't have any restrictions on t, so t can be any real value. So what we learned is x is only positive, but y can be positive and negative. So this is useful when we rewrite our expression. So natural tendency is to use this here to write, because here we have x equal t squared, so here is t squared times t, right? So it's x times radical x, so we'll have x to power 3 over 2. That's natural tendency. However, what we realize, yes, x is positive only, but y is also positive only. So this is not actually representing our parametric curve, because in this expression here x is positive and y is positive, so we are only on one part of the curve actually. So that's how we know that this is not the correct expression, because x is positive but y can be positive or negative depending on the values of t. So that's how we figure out that our natural tendency will produce something that is not actually the correct curve. It will just give us one branch of the curve. So we need to be wise. So here we rewrite this expression here, we isolate t and then we plug it into the value of x. So now this expression, x is positive, but y can be positive or negative. So now we have the right shape. So it is very important to realize from the beginning, it tells us something about our curve. So sometimes our natural tendencies will not produce the correct curve, because this Cartesian expression is not equivalent to this parametric expression. This one here is x equal y to power 2 over 3, that's fine. So these are just nuances to realize, yes, we can eliminate the parameter, but each time we eliminate the parameter, we lose some information. That's why we need to go back always to our parametric expression. It's easy probably to just plug different values of t and then have a couple of dots and connect them. That would be an easy thing to do just to save us any problems. So we can do that always. You don't need to go through the Cartesian expression. Here similarly we have x equal cosine and y equals secant square. Secant is 1 over cosine, so secant square is 1 over cosine square, which is 1 over x squared. So immediately we got an expression that is more familiar to us, so we can sketch it quickly. And then the parameter goes from 0 to pi over 2. So the starting point is at 0, so cosine 0 is 1, and here we have also 1, so we will have starting point here. And as we move to pi over 2, x is going towards 0, but y is exploding. So as we go to pi over 2, x is going towards 0, but y is exploding. So we are going this way on the branch. Here another one, what we see here is x is exponential minus t and y is exponential t, so essentially y is 1 over x. Now what we realize, that's cute, but y over x is defined everywhere except at 0, so we could think of two branches, but here we need to go back. Exponential is always positive, so x is positive, y is positive. So we are only on one branch of the y over x, only in the first quadrant where x is positive and y is positive. And that information is written here, encoded directly into the parametric expression. So we have this part of hyperbola that is in the first quadrant only based on the information here. So yes, y equal 1 over x helps us get the general shape, but we need to go back to the expression, to the original expression, to figure out on which branch we are. Another example again. Here t is positive, so we know that now x starts at 2 and goes up. So x starts at 2 and goes up. And y, when t is going towards 0, y is exploding, right? So closer we are at the beginning, y is big. So essentially closer we are to x equal 2, bigger the y, so we are starting from here and going down, we have an asymptoted 2. So that's easy to guess. Now we could obviously rewrite this quickly, write t as x minus 2 and then y is 1 over. So that gives us an expression. Another interesting thing, log, and now t starts at 1, so x starts at 0 and y starts at 1, so x 0, y 1, and then bigger the t, bigger the x, bigger the y, so we are going up. Now what is the shape of the curve? Well, from here x is equal to ln t, so how do we get t? We take exponential, so t is exponential x, and we plug it here now in y, so we have y is radical of exponential x, so exponential x over 2. So that's the shape of the curve, and we know that we start at 0.10 and we go up. So those are just curiosities to get the direction of the movement and then some restrictions on the curve. Here similarly x is absolute value of t, so any value of t is possible, but x will be only positive. And here y is absolute value of 1 minus absolute value of t. Obviously we can replace t by absolute value of t by x, so we get an expression like this. So absolute value is always positive, so our y will be 0 and bigger, and here x also will be 0 and bigger. So essentially we get an expression like this, in which x is positive and y is positive. So it's absolute value here helps us draw the first part. So x is positive here and y is positive, so that's why we stop at this point. At t0 we have x0 and y1, so x0, y1, so this is the starting point. And as t increases, x goes to 1, y goes to 0, so we go this way and then it goes this way. So now what happens when t is negative? Well, we still have absolute value, so it goes the same way anyways. An interesting case here, x is sine square and y is cosine square. So x plus y is sine square plus cosine square, which is 1, right? So we have immediately an equation of a straight line, like y equal 1 minus x from here. But what we realize is sine square is positive, cosine square is positive, but sine square is between 0 and 1, and cosine square is also between 0 and 1. So x is run from 0 to 1 and y is run from 0 to 1 only. So even though our Cartesian expression is y equal 1 minus x, which is a straight line, fine, but we are constrained only to x's between 0 and 1 and y between 0 and 1. So at t equals 0, x is 0 and y is 1. So we are here, and then as t increases we go down and then we go back up. So essentially this is the part of the curve y equal 1 minus x that we are interested in, because that's the only part that is represented by this parametric equations here. So our plane curve is just this part here. So eliminating the parameter, yes, it helps us give a general expression, but we need to go back to the definition of x and y to figure out the limitations, the restrictions. So there are plenty of exercises for you to solve, to have some fun, and you have also the solution manual. So this part here is quite straightforward. We can take the parametric expressions for x and y and just for each value of t get corresponding values of x and y and then draw those points on the xy plane and then connect them and we get the shape. Another option is, whenever possible, maybe eliminate the parameter and then get an expression y equals some expression of x or x equals some expression in y that is maybe more familiar to us, to get a general idea of the shape of the curve, and then we go back to the definition of x and y to see which part of that curve actually is our parametric or plane curve. So in general, this part is quite straightforward.